Okay, in this video we're going to be looking at two dependent samples, and this time we're going to be looking at matched pairs. So here we're going to be testing the claim, or methods for hypothesis testing and constructing confidence intervals that involve the mean and differences of the values from two dependent populations. Now in another video we looked at independent samples where the sample values from one population have no relationship with the sample values of the second population. Now here, when we're dealing with dependent samples, there will be a relationship or some relationship whereby each value in one sample is paired with a corresponding value in the other sample. Okay? And this is where matched pairs come in. Okay, and I'll share this with you. Here, because the hypothesis test and confidence interval use the same definition and standard error, they are equivalent in the sense that they result in the same conclusions. Consequently, the null hypothesis that the mean difference is 0 can be tested by determining whether the confidence interval includes 0. Okay. Now, we don't have any exact procedures for dealing with dependent samples, but we can use the t-distribution as a reasonably good approximation, so the following methods are going to be commonly used. Okay. Alright, first of all, I'm going to introduce to you some notation that's going to be used when we test a claim or do a confidence interval that involve the mean and the differences of the values from two dependent populations. D, lowercase d, is the individual difference between the two values in a single matched pair. So you'll be given various number of matched pairs. What you're going to do to find the difference is you'll subtract the first value minus the second value to get each individual difference. Mu sub d, that's going to be the mean value of the difference from the population of all the pairs in that data. So you'll be looking at all paired data, and that would be mu sub d. D bar is going to be from the sample data. That's going to be the mean value of the differences for the paired sample data. And then S sub d, again, that's going to be from the paired sample data. That represents the standard deviation of the differences for the paired sample data. And lowercase n is the number of paired data. Okay? So you have to count the number of paired data that's given to you, and not the individual numbers that are in that paired data. Okay? So, you know, you'll have paired data, meaning that you'll have a pair of data values here. So you have to count the number of paired data. Now, there are three requirements when you're testing a claim or doing a confidence interval. Number one, the sample data are dependent. Okay, I've already talked about what dependent means. That you have a relationship where each value in one sample is paired with a corresponding value in the other sample. Number two, simple random samples. The samples have to be simple random samples. In other words, samples of the same size has an equal chance of being selected. And then number three, either or both of these conditions must be satisfied. That means this: the number of paired data of sample data is large. Typically, n has to be bigger than 30. That's the number of paired data has to be bigger than 30. Or the pairs of values have differences that are from a population having a distribution that is approximately normal. So once those three requirements are met, you can do a hypothesis test or construct a confidence interval. Okay, now what I'm going to do is give you the hypothesis test statistic for dependent samples that you'll use. So this is the hypothesis test statistic for dependent samples. And here we're going to use a t-test statistic. And that's going to be equivalent to this. D bar minus mu sub d, all that's divided by s sub d over the square root of n. Okay, now this test statistic will be used where the degrees of freedom and that's going to be df equals n minus 1. So you're going to have n minus 1 degrees of freedom here. And of course your d bar is going to be your sample mean of your differences. Mu sub d is the population mean of all the differences. S sub d is the standard deviation of the individual differences in that particular sample, and n is the number of paired data. Okay. Now, most likely you'll be using a p-value approach. For the p-values, you have to use, I would prefer using technology. And in this video, we're going to be using the TI-83 or the 84 plus calculator to find those p-values. Okay. Now for the critical value approach, since it is a t-test that we have, we're going to use table A-3. And in this case, that's going to be the t distribution table. Now, I believe we used this before when we were testing a claim about a population mean, where the population standard deviation was unknown. So you had to use this table right here. On the left-hand side is your degrees of freedom. The top rows are the area in one tail and the area in two tails. If you have a left tail or a right tail test, you'll use this row, which is the area in one tail. For a two-tail test, you'll use the area in two tails row. And from that will help you get your critical t values. Okay. Now the other thing I'm going to give you is the confidence interval for dependent samples. Confidence interval for dependent samples. And that format for the confidence interval for dependent samples will be this. That would be d bar minus e, and that's less than mu sub d, and less than d bar plus e. And this is going to be where E, which is of course, if you recall, that's your margin of error. That will be T of alpha over 2. That's usually your critical value times S sub D. That's the standard deviation of your individual differences divided by the square root of n. So this E right here represents the margin of error. T of alpha over 2 is your critical value. And we've already talked about what S sub D is. That's the sample standard deviation of your individual differences. N is the number of paired data. Okay. So to find your critical values for t of alpha over 2, you can use table A-3, and you're going to use that table with n minus 1 degrees of freedom. Okay. So your critical values for t of alpha over 2 will be coming from table A-3 that I just showed you earlier. That's going to be your t distribution table with n minus 1 degrees of freedom. Okay. So now let's look at some examples that are related to just this. Alright, so now let's start with this first example that I have here. Okay, here we go. Assume that the paired data came from a population that is normally distributed. Using a 0.05 significance level, find d bar, S of d, the t-test statistic, and the critical values to test the claim that mu sub d equals 0. And this right here is an equal sign here that I need to mention. And here you have xi and yi. These are your x and your y values. So here these are your paired sample data. Now in this case here, first of all I'll have to find out what d is and d squared is, because there are a couple of formulas that I'm going to need to use here. D bar is the mean of all your differences in this sample. That's going to be the sum of your d, which is your differences, divided by n. N is the number of paired data. And then also we have S of d, which is your sample standard deviation of your differences. That's going to be the square root of n times the sum of all your d squares minus the square of the sum of all of your d's divided by n times n minus 1. Now, you might have to recall back on the video for section 3-3 where we did the measure of variation, where I introduced the standard deviation. In this case, we use x's here. This case, we're using d's, d squared and d. And then for the mean, we talked about that in the video for section 3-2, where we talked about the measures of center. We use x here. In this case, we're using d, the sum of your differences. Okay, so here we have to find two things: d, which is your individual differences, and then we're going to square each individual difference. That's your d squared. Okay, so let's do this. Here what I'm going to do here is subtract the first minus the second. I'm going to subtract x minus y to get the d on each of these paired data values. Starting with this one, 8 minus 12, that's negative 4. Now your differences can be negative or positive. In this case, this next pair of data, 15 minus 14, that will be 1. This next pair of data, 8 minus 7, is also 1. This next one, 19 minus 15, will be 4. This next one, 9 minus 8, that's going to be 1. This next pair of data, 6 minus 1, is negative 5. This next one is 12 minus 8, will be 4. And the last one, 18 minus 15, will be 3. And what I'm going to do here is go ahead and take the sum of these individual differences here. That's going to be the sum of d And by the way, that Greek letter sigma, capital letter sigma, that represents the sum. So if I do negative 4 plus 1 plus 4 plus, negative 4 plus 1 plus 1 plus 4 plus 1 plus negative 5 plus negative 5, that should be plus 4 plus 3. That sum will be 5. So the sum of all of your differences will be 5. And then d squared, I'm going to square each individual difference that I came up with. So like for negative 4, if I squared, negative 4 times negative 4, that's 16. For the 1, 1 squared will be 1. 1 squared again will be 1. 4 squared is 4 times 4, that's 16. 1 and you squared will be 1. Negative 5, if you squared negative 5 times negative 5, that will be 25. 4 and you squared 4 times 4 again, that's 16. 3 and you square that, 3 times 3 will be 9. I'm going to go ahead and get the square of the differences here, or the sum of all of my squared differences. So in this case here, add 16 plus 1 plus 1 plus 16 plus 1 plus 25 plus 16 plus 9. I'm going to get 85. So the sum of all the d squares will be 85. Okay. Now from this I can find out what d bar is, and I can find out what s of d is going to be. Now d bar is the sum of all the differences divided by n. N is the number of paired data. The sum of all the d's was 5. So this would be 5 divided by the number of paired data. I have 8 paired data values. So I'm going to divide by 8. Now I'm not dividing by 16. I'm not counting each individual number that I see here. I'm counting the number of paired data. And there are 8 pairs of data. So it's 5 divided by 8, which will be 0.625. Just take the 5, divide that by 8 on the calculator, and you'll get that decimal value of 0.625. Now for the S of D, that's the standard deviation of your differences. That's going to be that formula up here. Now we write that, which is the square root of n times the sum of all your squared d's minus the square of your d's, and that, the sum of your d's, and it's going to be squared, all divided by n times n minus 1. So n is the number of paired data, which is your 8. So I'm going to have the square root of 8 times the sum of all your d's, d squared, the sum of your d squared, that's 85. Minus the sum of your d's, that's 5, so that's going to be 5, and then that exponent of 2 means I have to square that 5. Minus n is 8, so that's 8 times 8 minus 1. Now what I'm going to do here is simplify what's underneath this radical first. And whatever I get underneath the radical, I'll take that value and take its square root. So in this case here, let me clear this out. That numerator is going to be in parentheses. So I'm going to use my left parentheses key, then type in 8 times 85 minus 5, and then hit the x squared button to square the 5, and then close the parentheses. And then that's going to be divided by, now the denominator, I can do this mentally. If I do 8 minus 1, that's going to be 7. 7 times this 8 on the outside would be 56. So I can just go ahead and type in the 56. And that's to save some keystrokes here. And then hit enter. So this will be 11.696.42857. And all that's underneath the radical. And then I'm going to go ahead and take its square root. So to do the square root, you have to press the second and the x square button. Second and x square will give you the square root. But if I want to retrieve this answer, all of this decimal value, I'm going to press second, and then there's a button that has the negative key. Right above it is the word ANS for answer. So I press that key. Because what it's going to do is take that previous answer and I'll get the square root of that previous answer. Then hit enter. And in this case here, this will be to 3 decimal places, 3.420. So 3.420 will be the standard deviation of the individual differences of that particular sample. Okay. Now, using this information, I can calculate the test statistic. And I'm going to calculate the t-test statistic. So here, I'm going to use that t-test statistic, which is t is equal to d bar minus mu sub d. All that's divided by s sub d over the square root of n. Okay, so in this case here, d bar was 0.625. So here I'm just substituting those values into this formula, minus mu sub d. Now you're testing the claim that mu sub d equals 0. So that's what mu sub d is going to be equal to 0. So I'm going to put 0 in its place, divided by s sub d was 3.420. Substitute that. That's over the square root of n, which is your 8. N is the number of paired data. Now, what I'm going to do here is put the numerator and the denominator in parentheses and use my graphing calculator to calculate what my t-test statistic will be. Okay. So here, I'm going to type in the left parentheses key, type in 0.625 minus 0, close parentheses, divide that by, then left parentheses, s sub d, which is 3.420, divided by, then second and x squared for the square root, second x squared for the square root, and then 8. Then hit your right arrow key to get out from underneath the radical, and then close your parentheses. Now, if you're using a TI-83 for the square root, you'll have to close your parentheses for the square root, and then close it again to close the parentheses for this first one that you entered for your denominator, and then hit enter. And that t-test statistic to 3 decimal places will be 0.517. So your test statistic for this sample data will be 0.517. Okay, now they ask for one more thing, and that's the critical values to test the claim that mu sub d is equal to 0. Alright, now let's think about this. I'm going to write the null and the alternative hypothesis. If mu sub d is equal to 0, it has to fall under the null hypothesis. And that's because the null always has an equal sign in it. Your null hypothesis always has the equal sign in it. So your alternative hypothesis will have to be the opposite of your equal to, which is not equal to. So mu sub d is not equal to 0. And I wrote this because I want to find out what type of test I'm going to have. And I have to look at the alternative hypothesis to determine what type of test I'm going to have. Since it's not equal to, I have a two-tailed test. Now, had that been less than or greater than, I would have a one-tailed test. But in this case, for not equal to, it is a two-tailed test. And I'm also going to find out what my degrees of freedom is by doing n minus 1. N is the number of paired data, that's 8. Subtract 1 from 8, you're going to get 7. And my alpha level is 0.05 because in the problem, I'm asked to use a 0.05 significance level. So the alpha level will be 0.05. So I need to find out what the critical t-value is, which is t of alpha over 2. And this is where I use table A-3, or the t distribution table, for critical t-values. And looking at this, I have 7 degrees of freedom, and I'm looking under the row that says area in two tails because it is a two-tailed test. So here's 0.05. Because I'm told to use a 0.05 level of significance. So here's 0.05, and it's under the area in two tails. So if you read across from 7 and down that column, you'll see that 2.365 represents your test statistic for 7 degrees of freedom at the 0.05 significance level in two tails. And since it is a two-tailed test, I must use plus or minus. So my critical t-value will be plus or minus 2.365. And why did I use the plus or minus? Because it's a two-tailed test. For a right-tailed test, it will just be the positive part. For a left tail, it would be negative. And for two-tailed, plus or minus. Okay. So that was the first example. Alright, now let's look at the second example here. Listed below are ages of actresses and actors at the time they won an award for the categories of Best Actress and Best Actor. Use the sample data to difference between the ages of actresses and actors when they win the award. Use a 0.01 significance level. Assume that the paired sample data is a simple random sample and that the differences have a distribution that is approximately normal. Okay, so here we have our paired data for actresses' age and actors' age. We need to find what D is, the difference, and then we need to square those individual difference. Okay, because I need to find the mean of the individual difference for that sample and the standard deviation of the differences for that particular sample. Okay, so let's find out what D is. Subtract the first minus the second. 19 minus 40. That's negative 21. The next one, do 32 minus 49. That's negative 17. The next one, 27 minus 63. That's negative 36. The next one, 55 minus 50. That will be 5. And then the next one, 31 minus 39. Negative 8. I'm going to go ahead and find the sum of those individual differences here. So in this case, if I do negative 21 plus negative 17 plus negative 36 plus 5 plus negative 8, that will give me negative 77. So the sum of the individual differences is negative 77. And then for D squared, I'm going to square each individual difference. Okay, So if I square a negative, it's going to be positive. So negative 21 squared will be a positive 441. The same thing here, negative 17 and u squared will be 289. For negative 36, if you square that, that would be 1,296. For 5, square the 5, you're going to get 25. And then negative 8, you square that negative 8, you're going to get positive 64. And then I'll go ahead and get the sum of all these d squares. So in this case here, 441 plus 289 plus 1296 plus 25 plus 64. That will give you the sum of all your d squares being 2,115. Okay. Now I need to find out what d bar is going to be. D bar is the mean of all the differences for that sample, and that's the sum of your d's divided by n. The sum of your d's was negative 77. And in this case, you got 1, 2, 3, 4, 5 paired data. So that's negative 77 divided by 5, which would be a negative 15.4. So the mean of your differences for that sample will be negative 15.4. And then S of D is where we use that formula of n times the sum of your d squares minus the square of the sum of all of your d's divided by n times n minus 1. So here I'm going to substitute those values into that formula here. So I have the square root of n, which is 5, that's the number of paired data, times the sum of your d squares, that's 2,115, minus negative 77, which is the sum of your d's, and that's going to be squared. All that's divided by n, which is 5, so that'll be 5 times parentheses 5 minus 1. Now I'm only going to simplify what's inside the underneath the radical. Then whatever that is, I'll finally take that square root. Okay, so here's what I'm going to do here. The numerator will be in parentheses, and that's going to be 5 times 2,115 minus, now for the negative 77, that needs to be in parentheses. So left parentheses, negative 77, close your parentheses around the negative 77, and then you square it. Had I left those parentheses off, I would have gotten the wrong answer. Because what it will do here is take the 77 and square it, and whatever that is, it'll give it the sign of the negative number. And then I'm going to close the parentheses, because I opened the parentheses right here to begin with. So all of this will be divided by, now let's do this denominator mentally. Well, I got 5 parentheses, 5 minus 1. If I do 5 minus 1, that's going to be 4. 4 times this 5 that's in front would be 20. So your denominator there will be 20. Then we're going to hit enter. And this will be 232.3. So I'm going to take the square root of 232.3. And to do that, second x squared for the square root. I can go ahead and type in 232.3. Or you can hit second and the negative key to get that answer. To pull up that answer. It'll take that previous answer and just find its square root. Then I'm going to press enter. Correction. Second x squared, 232.3. That would make a big difference. That would be 15.241. So the standard deviation of the differences for that particular sample will be 15.241. So I have to find out what my preliminary information is, because I'm going to need that in order to conduct the hypothesis testing and calculate the test statistic as well. So let's start off with step number 1. And that's writing the original claim in symbolic form. Now we're testing for a difference between the ages of actresses and actors. So we want to find out if there's a difference. We have to use the not equal to. So it'll be mu sub d is not equal to 0. Here it doesn't give any type of directional language, whether less than or greater than. So we have to use not equal to. So the original claim will be mu sub d is not equal to 0. Now step number 2 is the opposite of the original claim. And that is, the opposite of not equal to will have to be equal to. So here mu sub d equals 0. And from steps 1 and 2, step number 3, we can write our null and alternative hypothesis. The one that does not have equality will be the alternative hypothesis, and that will be this one right here. Mu sub d is not equal to 0. And that will be the claim. And of course mu sub d equals 0, because the null always has equality in it. It always has the equal sign. Now step number 4 is the level of significance, or the alpha level. In this case, we're told to use a 0.01 significance level. Yeah, use a 0.01 significance level. So your alpha level here in step 4 is 0.01. Now step number 5, we're going to go ahead and calculate the test statistic. So here, this is where we use that T formula for your test statistic, which is d bar minus mu sub d. All that's over S sub d over the square root of n. Now we're going to substitute values into this formula here. The d bar was negative 15.4. That's what we calculated from the start, negative 15.4. Now notice I started off by finding out what d bar is and S sub d was to begin with, because I have to do that in order to calculate my test statistic. So it'll be negative 15.4 minus mu sub d is going to come from your null hypothesis. In this case, mu sub d is 0. All that's divided by S sub d was 15.241 divided by the square root of n. N was 5 because there were 5 paired data values. Okay, now in this case here we're going to put the numerator and the denominator in the parentheses so we can use our graphing calculator to find out what that test statistic is going to be. Okay, so in this case here, the numerator will be in left parentheses, negative 15.4 minus 0, close your parentheses, divided by, and then left parentheses, 15.241 divided by, then second x squared, and then 5. Now, the right arrow key gets you out from underneath the radical, but for the 83 you have to close your parentheses for the square root, and then you have to close it again like I'm doing here on the 84 plus to close out the parentheses for this first one that we opened. And then we go ahead and press enter. And that will be my test statistic here. And I'm going to round this test statistic to 2 decimal places. So this will be negative 2.26. Now on your homework, make sure that you do round off to whatever decimal place that they ask for. Okay? So my test statistic here is negative 2.26. Now step number 6 is calculating the p-value. And it will be easier for me to use the graphing calculator to do this. And I'm going to show you how I'm going to do this on the graphing calculator. What I'm going to do here is use the row that has the individual d values here that you see here. And I'm going to put those values in this graphing calculator. So, what I'm going to do here, press the stat key. Now I'm putting new data values in, so I'm going to select number 1 for edit. Now if you have any data values in your L1, what you want to do here is press your up arrow key to highlight L1, and then press the button that says clear, and press the button at the very bottom that says enter. What that will do, it will clear out all those data values in L1. And what I'm going to do here is enter each of these individual differences in L1. So here, starting with the negative 21. And I'm going to press enter after each data entry. Then negative 17, enter. Then negative 36, enter. Then 5, enter. Finally, negative 8, and enter. So you have to press enter after each individual data value, including the last one. So those data values are in L1. The next thing I'm going to do here is press the stat key. Then I'm going to use my right arrow key to highlight the test menu. Now the one that I'm going to select here, since it's a t-test, I'm going to select number 2, which just says, obviously, t-test. So I go down to number 2 and press enter. Now, if your stats is highlighted, what you want to do here is highlight data, because you have data values. You don't have the sample statistics. You have data values. So what you want is to put the blinking cursor on top of data and then press enter to highlight data. Now, pressing the down arrow key, mu sub 0 is 0, so that's going to remain the same. That's the same as your null hypothesis. For list, L1 will remain the same. If you use L2 or L3, what you have to do here is press second and number 2 for L2, or second and number 3 for L3. But since I have it in L1, I'm not going to change this. The down arrow key, the frequency remains the same. Now, for the mu, you're going to have 3 choices, either not equal to mu sub 0, less than mu sub 0, or greater than mu sub 0. You'll have to look at your alternative hypothesis. In this case, we have not equal to 0. So we have to select the one that says not equal to. And what you'll have to do is put the blinking cursor on the one that is related to the alternative hypothesis and press enter. Okay, and I have that already done, because this is already highlighted. Not equal to mu sub 0 is already highlighted. Now, hit your down arrow key to highlight calculate, and then press enter. Now you'll see that your test statistic is the same as what I got when I did this using the t formula for your t-test statistic. That's this, and it's rounded to 2 decimal places, negative 2.26. The p-value is right underneath it. That's this number right here. And I'm going to round this off to 3 decimal places. That will be 0.087. Okay. And while I have this up here, you'll see that your x bar was negative 15.4, which is what I have there. when I did that manually. S sub x, that's the sample standard deviation of your differences. That's 15.241. And n is the number of paired data, that's 5. Okay? So my p-value there is 0.087. Now, step number 7 is a decision rule. And that's this. If your p-value is less than or equal to alpha, you want to reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. And then we're going to look at 0.087, that's my p-value. The alpha level was 0.01. So we're going to compare those two. You can see that 0.087 is greater than 0.05. No, 0.01. So in this case here, doesn't follow the decision rule, so we have to fail to reject the null hypothesis. So we're failing to reject the null hypothesis. And step number 8 is writing the conclusion statement using simple non-technical terms. The claim was the alternative hypothesis. We failed to reject the null. So that means that we cannot support the claim. So here there is not sufficient evidence to support the claim. That there is a difference between the ages of actresses and actors when they win the award. Okay. So all of that is that particular hypothesis testing. So basically you have to find out what your mean of your differences are. Well, you have to find out what your differences are, and then find out what the square of your individual difference, and then you find the mean and the standard deviation of your differences for that particular sample. Okay. Okay, now let's look at example E3. This one, you're going to construct a confidence interval estimate. Okay. The data below are yields for two different types of corn seed that were used on adjacent plots of land. Assume that the data are simple random samples and that the differences have a distribution that is approximately normal. Construct a 95% confidence interval estimate of the difference between type 1 and type 2 yields. What does the confidence interval suggest about Farmer Joe's claim that type 1 seed is better than type 2 seed? Okay, so here we can use the confidence interval estimate to test a claim. Now, when we do a confidence interval, if that confidence interval estimate, well, if that confidence interval includes 0, where the lower limit is negative and the upper limit is positive, then that means that there is no sufficient evidence of a difference. That's automatically failing to reject the null hypothesis. But if it does not include 0, if both the lower and the upper limits are negative, or if both the lower and upper limits are positive, then there is sufficient evidence of a significant difference. And this is what we have right here, type 1 and type 2, and those data values here. Okay, we need to find out what D is, and we need to find out what D squared is going to be. Okay, because we don't know what D bar and we don't know what S of D is. Now, here I'm going to subtract the data value of type 1 minus the data value of type 2. So in this case here, 2044 minus 2061, that's negative 17. This next one, 1993 minus 1907, that will be 86. This next one, 2082 minus 2063, will be 19. The next one, 2462 minus 2426, will be 36. And then this next pair of data, 2169 minus 2195, that will be a negative 26. The next one, 1999 minus 1984, that's 15. The next one, 2293 minus 2191, that's 102. The next one, 1410 minus 1448, that would be negative 38. Now I'm going to go ahead and take the sum of those different individual differences. Okay, so I'm going to have negative 17 plus 86 plus 19 plus 36 plus negative 26 plus 15 plus 102 plus negative 38. That sum is 177. So the sum of your differences here, that's 177. And then I'm going to take the square of each of these individual differences here. So negative 17 and u squared, negative 17 times negative 17, that's a positive 289. 86 squared is 7396. 19 squared, that's 361. 36 squared, that's 1296. Negative 26 squared, that's 676. That's negative 26 times negative 26. 15 squared is 225. 102 squared is 10,404. And negative 38 squared is positive 1444. Now I get the sum of all the d squares. So if I add 289 to 7396 to plus 361 plus 1296 plus 676 plus 225 plus 10,404 plus 1444, that would be 22,091. So the sum of all your d squares is 22,091. Okay, now I'm going to find out what d bar is going to be. D bar is this. That's the sum of your d's divided by n, and the sum of all your differences was 177 divided by, now there are 8 paired data. 8 paired data. So it'll be 177 divided by 8, which will give you 22.125. So that's what d bar is, the sample mean of your differences for this sample. Okay, now S of d, that's the standard deviation of your differences for this sample. That's the square root of n times the sum of your d squares minus the sum of your d's, that's going to be squared, over n times n minus 1. N is the number of paired data, that's going to be 8 times the sum of your d squares, that's 22,091, minus The sum of your d's, that's 177, and that's squared. All that's over n, which is 8 times 8 minus 1. Okay. Now I'm going to simplify what's underneath the radical, and then whatever I get for that, I'm going to take its square root. Okay, the numerator will be in parentheses, so it'll be 8 times, so I have left parentheses 8 times, 22,091 minus 177, then you're going to hit your x squared button to square it, then close your parentheses. Then divided by, now, if I have 8 minus 1, that's going to be 7. 7 times the 8 that's in front would be 56. And then close your parentheses. So this will be 2,596.410714. And I'm going to take its square root. So I'm going to have second and x squared for the square root. And I'm going to go ahead and retrieve this answer and put that underneath the radical. So I'm going to press the second and the negative key, which is at the very bottom of your calculator that has ANS above it. So second and negative for your answer. Because you want that answer, you want to take that answer and find out what its square root is going to be. Then press enter. Let's say the 3 decimal places. This will be 50.955. So the standard deviation, S of D, would be 50.955. Okay. Now I'm doing a 95% confidence interval. So this is going to be some information that I'm really going to need. Okay, now let's first do this. I'm dealing with a 95% confidence interval. That means this alpha level will have to be 1 minus the confidence level, which is 0.95, written as a decimal. So 1 minus 0.95 is going to give me 0.05. So that alpha level there will be 0.05. Also, my degrees of freedom is n minus 1. There are 8 paired data, so that means 8 minus 1 will be 7. Now those 2 pieces of information I'm going to use to find the critical t-value. So this is where I use the t-distribution critical t-values table, or table A-3. Here I got 7 degrees of freedom, and I'm only looking at the row that says area in 2 tails for a confidence interval. Only for a confidence interval is when you use the area in 2 tails row. And that alpha level was 0.05. So 7 and 0.05, if you look across and down, you'll see that that critical t-value will be 2.365. So your critical t-value is 2.365. Okay, and then I'm going to find the margin of error using t of alpha over 2 times s of d over the square root of n. Now you see why it's important to find s of d, because you're going to have to find out what s of d is to find out what your margin of error is. T of alpha over 2 was 2.365 times the s of d was 50.955 over the square root of n. N was 8. So here we can type all this in the calculator. If I have 2.365, multiply that by 50.955, that's going to be divided by second x squared for the square root of 8. And then hit enter. My margin of error to 4 decimal places will be 42.6062. 42.6062. Okay. Now I know what the margin of error is. I know what D bar is. Those are the two pieces of information I need to construct my confidence interval. And the format for the confidence interval, if you recall, is D bar minus E, that's less than mu sub D, and less than D bar plus E. And D bar was 22.125 minus the margin of error of 42.6062. That's going to be less than mu sub D and less than. I'll copy over those same data values, but well, those same numbers, but it'll be a plus sign. Okay, and if I do 22.125 minus 42.6062, I would get a negative 20.48. That's less than mu sub D and less than, add those two, be 64.73. Okay, so that's your confidence interval here. Okay. And if we were to interpret that, then we can say here that we are 95% confident that the true mean value of the differences for those type 1 and type 2 yields would be between negative 20.48 and positive 64.73. Okay. Now, based on that confidence interval, I see that my lower limit is negative and the upper limit is positive. So that means that the confidence interval does include 0. So we can say here that there is not sufficient evidence to support Farmer Joe's claim. And his claim was that type 1 seed is better than type 2 seed. But here, our confidence interval has 0 in it. The lower limit is negative, the upper limit is positive, so that means 0 is included. Okay. Okay, I'm going to do another example that has a hypothesis testing in it. Okay. I'm going to do this one, and then I'll do one more that has a confidence interval. Data on the numbers of hospital admissions resulting from motor vehicle crashes are given below for Fridays on the 6th of a month and the Fridays followed on the following 13th of the same month. Assume that the paired sample data is a simple random sample and that the differences have a distribution that is approximately normal. Construct a 95% confidence interval of the mean of the population differences between hospital admissions. Use the confidence interval to test the claim that when the 13th day of the month falls on a Friday, the number of hospital admissions from motor vehicle crashes are not affected. And here's what we have here. The data values for Friday the 13th, the 6th, and also Friday the 13th as well. Okay, now what I'm going to do here is get the differences of each one of these paired data and then square those as well. Okay, so for each data value, subtract the first minus the second. So here's 6 minus 14 is negative 8. The next one, 9 minus 15, that's negative 6. The next one, 6 minus 14, that's negative 8. Here, 9 minus 12, that's negative 3. And then the last pair of data, 3 minus 12, that's negative 9. And I'll take the sum of your differences here. And this is going to be a negative number because all of my data values are negative. So if I add negative 8, negative 6, negative 8, negative 3, negative 9, you should get negative 34. Okay, let me see if I can write that a little bit smaller so you can see this. Okay. The sum of your d's is negative 34. Now we're going to square those d's. For d squared, negative 8 squared is 64. Negative 6 squared is 36. Negative 8 squared, that's 64. Negative 3 squared, that'll be 9. And then negative 9 squared is 81. And the sum of your d squares, if you add 64 plus 36 plus 64 plus 9 plus 81, you'll get 254. So the sum of your d squares will be 254. Okay. Now next I'm going to find out what d bar is. That's going to be the sum of your d's divided by n, which is the number of paired data. The sum of your d's, we found that out to be negative 34. And there were 5 paired data. 1, 2, 3, 4, 5. So negative 34 divided by 5 will be a negative 6.8. So your sum of your differences for this particular sample will be negative 6.8. And then S sub d would be the square root of n times the sum of your d squares minus the sum of your d's, and that's squared. All that's divided by n times n minus 1. Now the n is your 5, that's the number of paired data, times the sum of your d squares, that's 254, minus the sum of your d's, that's negative 34, and that's going to be squared. And n is 5, so that'll be 5 times 5 minus 1. I'm going to simplify what's underneath the radical, and then that answer, whatever I get for that, I'll get a square root. So I'll clear this out. Okay. The numerator will be in parentheses, so this will be 5 times 254 minus, now since I'm dealing with a negative number and it's being squared, I have to use the left parentheses for the negative 34 and close the parentheses around the negative 34 and then hit x squared. If I leave that parentheses out for that negative 34, what it's going to do is take the square of 34 and attach the negative sign to it. So negative 34 needs to be in parentheses. Then I need to close the parentheses because I opened it from the very beginning. Then divide that by. Do the denominator mentally. 5 minus 1 will be 4. 4 times 5 is 20. So you can just go ahead and type in 20. And then hit enter. So here, that will be 5.7 underneath the radical. But I need to take the square root of 5.7. So what I'm going to do is press second x squared for the square root. Now I just go ahead and type in 5.7. Let's see, this will be 2.38747. Just trying to use as many decimal places as I can here. Okay, we're dealing with a 95% confidence interval estimate, which is what we're constructing here. So, for 95% confidence, our alpha level will be 1 minus that confidence level, which is 0.95, written as a decimal. So 1 minus 0.95 would be 0.05. So the alpha level there will be 0.05. And also my degrees of freedom is n minus 1. There were 5 paired data, so that's going to be 5 minus 1, which will be 4. So I have 4 degrees of freedom and a 0.05 significance level in 2 tails. Because remember, with a confidence interval, confidence interval, we're dealing with 2 tails. And then we use table A-3 or the t-distribution critical values to find that critical value. So you always look under area in 2 tails for your confidence interval. And it was 0.05, which is right here in 2 tails. There were 4 degrees of freedom. So we read across and down, and this will be your test statistic right here, 2.776. So t of alpha over 2, your critical t value, is 2.776. Now we're going to use that along with our S sub d to find the margin of error. So E is equal to t of alpha over 2 times S sub d over the square root of n. And t of alpha over 2 is 2.776 times S sub d, which was 2.38747, divide that by the square root of n, which is 5. And then we type this in the calculator to find out what that margin of error is going to be. So here 2.776 times 2.38747 divided by second x squared for the square root, and then 5. And press enter. To 4 decimal places, this will be 2.96. The 6 will make that 39 or 40, so it will be 2.9640. So that's your margin of error, 2.9640. And I already know what D bar is. I have that. The margin of error is 2.9640. So here we can construct our confidence interval, which is D bar minus E, that's less than mu sub D, and less than D bar plus E. Now my D bar was negative 6.8 minus 2.9640, that was the margin of error, that's less than mu sub D, less than negative 6.8, this time is going to be plus 2.9640. Now if I do negative 6.8 minus 2.9640, I'm going to have negative 9.76. And I'm rounding the 2 decimal places here. Less than mu sub D, less than negative 6.8 plus 2.9640 would be negative 3.84, rounded to 2 decimal places. So this is what my confidence interval estimate is for the mean population of differences between hospital admissions. So here we can interpret that as saying that we are 95% confident that the true mean of the population of differences between hospital admissions falls between negative 9.76 and negative 3.84. Now in this case here, this confidence interval does not contain 0 because both the lower and the upper limits are both negative. So here we can reject the null hypothesis. Okay, since this does not contain 0, we can reject the null hypothesis. And reject the claim, but we can say that there is sufficient evidence to reject the claim that when the 13th day of the month falls on Friday, the number of hospital admissions from motor vehicle crashes are not affected. Okay, and that's because that confidence interval limit, that confidence interval does not contain 0. Those limits are both negative, so we can reject the null and reject the claim that when the 13th day of the month falls on a Friday, the number of hospital admissions from the motor vehicle crashes are not affected. Okay. So this is where we can construct that 95%, that confidence interval estimate, and then test that claim. Okay, one more problem out of this particular for this video. When subjects were treated with a drug, their systolic blood pressure readings in milligrams per Hg were measured before and after the drug was taken. Results are given in the table below. Assume that the paired sample data is a simple random sample and that the differences have a distribution that is approximately normal. Using a 0.01 significance level, is there sufficient evidence to support the claim that the drug is effective in lowering systolic blood pressure? Okay, and this is the data that we have before and the after. Okay, so in other words, you want the after to be less than the before. In other words, you want the differences to be bigger. Okay, because if you want the drug to lower your systolic blood pressure, then that means this before has to be bigger than the after. Okay, that's the way of interpreting that. But first we have to find out what d and d squared are going to be. That means we got to do the subtraction of each of these individual data values. Okay, well, each pair of data. So here for this one, 164 minus 148, that would be 16. 175 minus 162, that would be 13. 179 minus 147, that would be 32. 201 minus 150, that would be 51. 210 minus 179, that would be 31. 167 minus 177, that'll give you negative 10. 155 minus 156, that's negative 1. 181 minus 181, that's 0. 195 minus 176, that'll be 19. 158 minus 159, that's negative 1. 188 minus 179, that'll be 9. 203 minus 184, that'll be 19. So those are the individual differences here. Okay. And since I don't have enough space here, I'd have to write the sum of your differences here. If you were to add these individual differences together, you should get 178. So the sum of all your differences will be 178. Now we've got to square each individual differences here. So here, if I take 16 and square it, that'd be 256. 13, square that will be 169. 32 and you square it will be 1024. Square the 51, you'll get 2601. Square the 31, you'll get 961. Negative 10 and you squared is negative 10 times negative 10. That's 100. Negative 1 squared, negative 1 times negative 1, that's 1. 0 squared is 0. 19 squared is 361. Negative 1 squared that again will be 1. 9 squared will be 81. 19 squared is 361. And the sum of your d squares will be 5,916. Just simply add these data values together. Okay? We got to find out what d bar is going to be and s sub d. D bar is the sum of your d's divided by n. The sum of our d's was 178. N is the number of paired data. In this case, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 data values. So take 178, divide that by 12. Now I'm saying the two decimal places, 14.83. So the sum of you, well, the mean of your differences for this sample is 14.83. S sub d is the square root of n times the sum of your d squares minus the sum of your d's, and that's squared. All that's over n times n minus 1. So in this case here, your n, that's the number of paired data, that's 12. So I'm going to have the square root of 12 times the sum of your d squares, that's 5,916, minus 178, which is the sum of your d's, and that's squared, divided by n, which is 12 times 12 minus 1. Okay, so I'm going to do this in the calculator as well. Okay, the numerator will be in parentheses, so this will be 12 times 5,019 minus 178. Hit the x squared button to square it, then close the parentheses, and then divide that by. Now, let's think about this. 12 minus 1 is 11. 11 times 12 is 132. Okay? So that'll be divided by 132, which would give me 297.7879. 297.787. I'll go ahead and write it out loud. 78788. And then I'm going to take that entire answer and get its square root. So second x squared for the square root, and then second negative for the answer. I'm going to say 17.2565. Rounded to 4 decimal places. So that's the standard deviation of your differences for that sample. Okay, so I'll go ahead and start the hypothesis testing procedure, that 8-step hypothesis testing procedure, because those are the 2 pieces of information I'll need to start this off. So step number 1 is the original claim. Now we know we're going to have to use mu sub d. Now let's think about this for a moment. because we're trying to find out that the drug is effective in lowering blood pressure. That means we want our differences to be bigger. In this case, we want our differences to be larger. The before has to be larger than after. So that means we want our differences to be bigger. So mu sub d is greater than 0. Okay? So you want to be very careful how you write your original claim with this type of problem here, because it says lowering blood pressure. That means we want our differences for the before and after to be bigger than 0. So mu sub d is going to be bigger than 0. Step number 2 is the opposite of the original claim. The opposite of greater than will be less than or equal to. So be mu sub d is less than or equal to 0. Step number 3 is calculating the null and just writing the null and the alternative hypothesis from steps 1 and 2. One of these will have to be the alternative hypothesis, and keep in mind your alternative has only less than or greater than or not equal to, and it's this one right here. Mu sub d is greater than 0, and that's going to be the claim. The null always has the equal sign in it, so mu sub d equals 0. Step number 4 is the level of significance that we're dealing with in this case, and we're told to use a 0.01 significance level. So your alpha level in this case is 0.01. Now step number 5 is your test statistic. That's the t is equal to d bar minus mu sub d all over s sub d divided by the square root of n. That d bar, which we calculated earlier, was 14.83 approximately, minus mu sub d is from the null hypothesis, that's 0, all divided by s sub d. We found that out to be 17.2565, so let's use that, over the square root of n. And n is 12. That's 12 pair of data, so we have the square root of 12. We can type that in the calculator. Make sure that you put your numerator and your denominator in the parentheses. So here, left parentheses 14.83 minus 0, oops, close parentheses, divided by, and then left parentheses 17.2565 divided by second x squared for the square root, and then 12, right arrow or right parentheses for the square root, and then close your parentheses, then hit enter. To 2 decimal places, your t value will be 2.98. So the test statistic there will be 2.98. Now I'm going to do step 5 over here. Step 6 over here. Step number 6 is finding your p-value. Now here we can use the graphing calculator to do this, to get our p-value. What I'm going to do here is go back to this row where I have all my individual differences here. I'm going to type all of those in L1. Okay, so here I'm going to go to press the stat key. Then I'm going to select number 1 for edit. I got stuff in L1, so what I need to do is press my up arrow key to highlight L1, press clear, and then enter. That clears out all that data, all that stuff that's in L1. Now I'm going to enter these data values these individual differences that you see here. The row for the D's, that's your individual differences. One at a time. So I have 16, enter, 13, enter, 32, enter, 51, enter, 31, enter, negative 10, and enter, negative 1, 0, 19, negative 1, 9, and finally 19. Make sure you hit enter after each data value, especially the last one. And I'm only entering the row that has the individual differences. That's the D's. That's the D. Okay, next I'm going to press the stat key. I'm going to right arrow to test. And I'm going to select number 2, which is your T test. Down arrow to T test and then hit enter. Now data is highlighted as always. So here I'm going to have data highlighted. Mu sub 0 will be 0. I do have my data values in L1, so the list, which is L1, is there. Frequency will remain 1, but I need to look at my alternative hypothesis. Let me move the calculator and bring up this paper to find out which one I might need to select. I need to select either not equal to or less than or greater than. Well, looking at this alternative hypothesis, I'm going to have to select greater than. So I'm going to use my right arrow key to highlight greater than mu sub 0 and then hit enter to select that, because that needs to be highlighted. Then press the down arrow key to highlight calculate and then enter. Now you can see the test statistic is exactly the same as what I came up with in step number 5. Only difference was I rounded it off to 2 decimal places. Underneath it, you'll see the lowercase p, that's your p-value. And I'll round that off to 3 decimal places. That'll be 0.006. And let me give you a hint. Usually with your test statistic and your p-value, follow the directions of how many decimal places they want you to round off to. Okay? Very important. Follow the directions on how many decimal places they want you to round off to. So here my p-value is 0.006. Step 7 is the decision rule, where if your p-value is less than or equal to alpha, reject the null hypothesis. Now my p-value was 0.006. The alpha level that I'm using is 0.01. That's from step 4. Compare those two. 0.006 is less than 0.01. That does satisfy the decision rule, so we reject the null. Okay? And then finally, step number 8 is the conclusion. The claim was the alternative hypothesis. We rejected this null, so we're supporting the claim. So here we can say that there is sufficient evidence to support the claim that the drug is effective in lowering systolic blood pressure. Okay, so this right here represents your hypothesis testing for differences with matched pairs, as you can see here. Okay, so that's going to be concluding this particular video on 2 dependent samples when we deal with matched pairs.